Hello everyone, my name is Marina and today I am excited to present our recent work at AdaSense, which is adaptive low power sensing and activity recognition for wearable devices. A little bit about myself. So I'm currently working towards my PhD in electrical engineering at Brown University. I got my bachelor degree in computer engineering from Ain Shams University in Egypt in 2017. My research interests include machine learning, edge intelligence, and edge computing. So recently, wearable devices have attracted many researchers due to their wide applicability in different healthcare services like health monitoring and fitness. Our use case today is human activity recognition, and it has two main energy consuming components. The first one is the sensor, which is typically an inertial measurement unit. And the second part is data processing, which consists of feature extraction and activity recognition. The challenge here is that wearable devices are battery operated and they have strict energy and memory limitations. So AdaSense uses adaptive sensing to reduce the power consumption without sacrificing the accuracy. So this figure shows our proposed framework. So it has three main components. The first one is a motion detection sensor, which is an accelerometer. And then this accelerometer gives the data to our human activity recognition engine. And the output of the engine is activity. And then this activity is given as a feedback to our adaptive controller, which in turn takes a decision about the averaging window and the sampling frequency of the next episode. Now I'm going to talk about each component separately. I'll start by the sensor, then the adaptive controller, and finally the human activity recognition engine. So the motion detection sensor we are using is a BMI 160 energy measurement unit, and we are only switching on the 3-axis accelerometer. This is mounted on a microcontroller with a 32-bit ARM Cortex-M3 processor. So our sensor has two parameters, which are the sampling frequency and the averaging window. And the power consumption and the quality of the output signal depends on those parameters, meaning that if they are set to a high value, then the noise in the output signal would be low. Thus, it gives high recognition accuracy when parsed to the classification model. And the opposite happens when they are set to low value. So our question was, which sensor configuration should we choose in order to get the maximum energy accuracy trade-off? So to answer this question, we collected data at 16 different sampling frequencies and averaging window combinations. And we took those and we did a design space exploration as shown in the figure. So here the x-axis represents the current consumption per unit time, and the y-axis represents the recognition accuracy. We found that 4 configurations shown in as green diamonds dominated other points, forming a Pareto frontier for the energy accuracy trade-off. So we used those 4 points to design our adaptive controller. Our adaptive controller is based on a finite state machine, and the states are the Pareto frontier of the sensor configurations. The sensor starts by operating at the highest power configuration, and when the user activity is stable, meaning that the classification model predicts that the user has been doing the same activity for some time, the controller gradually switches the sensor to a lower power configuration till the activity changes with high confidence. So at that time, the sensor immediately switched to the highest power configuration. The final component of AdaSense is the activity recognition model. As we mentioned earlier, the input to our engine is the accelerometer data. It first passed by a buffer that stores 1 second of data to have an informative window for recognition. Then the data window is parsed to feature extraction to extract two types of feature. The first one is the statistical features, including the mean and the standard deviation. And the second one is few coefficients of the Fourier transform. Those features are then parsed to our classifier, which is a single neural network trained on data from 4 sensor configurations. And actually, this was crucial to prevent the loss in accuracy when switching to low power accelerometer data. Now I'm going to show a case study explaining the behavior of AdaSense. As we can see in this figure, the user was sitting for 60 seconds and then the user started walking for another 60 seconds. The above graph shows the accelerometer reading and the below graph shows the current consumption per unit time in microampere. So as we can see, at the beginning, the sensor was operating at the highest power configuration. And after 15 seconds, the sensor started to switch gradually to low power configurations. And it remained that way till at time 60 when the user started walking. The sensor switched immediately to the highest power configuration. And the scenario repeats itself as long as the device is on. Finally, we want to show our results compared to the previous work. So in the previous work, the authors used an intensity-based approach to adaptively change the configuration of their sensor based on the intensity of the activity. So with low intensity activities such as sitting, the sensor operates at low power configuration, while at high intensity activities like walking, the sensor operates at a high power configuration. The figure here compares the two works in terms of power and accuracy. So the dark blue bar represents the power of the intensity-based approach, while the light blue bar represents the power consumption of our approach. Also, the orange bar represents the accuracy of the intensity-based approach, while the yellow bar represents the accuracy of AdaSense. We did the comparison at 3 different user activity settings. In the low settings, the user changes the activity every 1 second, and in medium and high, the user changes the activity even more frequently, which is not actually what a normal user would do, but we wanted to test our approach at the boundary. As we can see, AdaSense reduces the power consumption by around 30% compared to the previous work, with negligible difference in accuracy. Also, it has less processing overhead because in our approach, we don't need to compute the intensity of the activity, which involves computing the derivative of the signal, which happens in the previous work. Moreover, AdaSense uses less memory as we use a single model, which is not the same as in the previous work, who use a separate model for each sensor configuration. Concluding this, using an adaptive controller, we dynamically switch the sensor to low power configuration depending on the stability of the user activity. We showed a design space exploration to the accuracy and energy trade-off of 16 different sensor configurations. AdaSense reduces the power consumption by 30% compared to the previous work, and it also reduces the power consumption by 69% compared to a static baseline that operates on the high power all the time. That's the end of my presentation. If you have any questions, I'm more than happy to answer.